All right, hello again, everyone. This is a video to go over the second FRQ set. This is only a single problem this time. It's sticking with the theme of rotational motion. So let me go ahead and get started with part A. So part A has two subparts. For the first one, they want you to draw a diagram illustrating the forces that are acting on this wheel as it's rolling down a ramp. So we have our enlarged version of the wheel on the right. So they want us to draw the forces, but also show where the forces are acting. Okay, so of course, with most objects, probably 99.9% of them, there's going to be a gravitational force. So that's going to be acting at the center of mass of the wheel. So it's going to start at the center of the wheel and it's going to point straight down. And we can label this as mg, that's the magnitude of the force. The other two forces are going to be from the surface of the incline. So remember, after gravity, the only types of forces that are possible are contact forces. This wheel is only in contact with one object, which is the surface of the incline. So the additional forces that are acting on it are going to come from the point of contact with the surface, which is this point right here. So there's going to be two forces. One is the normal force, which is going to be perpendicular to the surface. So the incline is going to push against the wheel in this direction. So this line should go right through the center. So I'll call that F sub n. And then there's going to be friction. Now, to think carefully about this one, which direction is the friction going to point? Now you may think since the wheel is going down the hill that the friction should point in the opposite direction of the motion, but that's not actually always true for rolling objects. So the way we want to think about it is think about it in terms of what's happening with the rotation of this wheel. So this wheel, as it rolls down the hill, is going to start rotating in this direction. So the rotation is caused by friction, which is creating a torque around the center of mass. So the friction has to point this way to cause a clockwise rotation in the wheel. So in this case, your intuition would have been correct that the friction was pointing up the hill, but just keep in mind that that's not always going to be the case, that the friction points in the opposite direction that the object is moving. All right, so for part two, they want you to briefly explain which of these forces causes the change in angular velocity of the wheel. So as I had just mentioned, the change in angular velocity requires a torque. So if you think about the torque caused by each of these three forces, you want to think about how far away the force is from the axis of rotation, which is right in the center of the wheel. So two of these forces, gravity and the normal force, act on a line right through the center of the wheel. So if you remember how we calculate torque, torque is equal to R times F times sine theta, where this R is sort of the distance from the line of action of the force to the axis of rotation. So if the line of action of the force goes through the axis of rotation, then R is going to equal 0. So for these two forces, there is no torque. But for the friction force, R is going to be this distance here, the distance from the line of the force to the center of the wheel. So there is a non-zero lever arm distance, so there's going to be a torque created by friction. So your answer to part A, subpart 2, can simply be that the friction force causes the change in angular velocity because it's the only force that creates a torque. Creates a torque about the center of mass of the wheel. All right, so for part B, they want you to do a little bit of calculation here to figure out what the acceleration of the wheel is. So they tell you that the friction force is not equal to the maximum value, but it's equal to 40% of the force or force component that's opposite the force of friction. All right, so what is the force or force component that's directed opposite to the force of friction? If you look at this figure here, opposite to the force of friction would be in this direction, down the hill. So the normal force does not have any component down the hill. It's perpendicular to that direction. But the gravitational force does have some component that points down the hill. And you may remember this from when we studied objects sliding down a hill, that this gravitational force can be separated into two components like this. And the component that is perpendicular to the surface is mg cosine theta, and then the component that's parallel to the incline is mg sine theta. So looks like I actually did not draw these forces correctly to scale, because friction force should be less than this downhill force that I just drew, but let's ignore that. So the friction force told is 40% or 0.4 times the force component that is opposite to the force of friction, which is mg times sine theta. Okay, so that means the net force down the hill then is going to be the downhill force, which is mg sine theta, minus the uphill force, which is 0.4 mg sine theta, and that is 0.6 mg sine theta. That is the net force. We know from Newton's second law that the net force equals mass times acceleration. So you can say the mass of the wheel times the acceleration equals 0.6 mg sine theta, or the acceleration is equal to 0.6 times g times the sine of theta. So that is our answer for part B. All right, so there's one final part to this problem. Part C asks you now to consider a block which slides down the same incline with no friction. And it asks you which of the two objects, the wheel or the block, will reach the bottom of the ramp with the greatest speed. So the answer to that is that the block is going to have the greatest speed. So why is that? They actually ask you to justify this two different ways. So first, they want you to explain your reasoning in terms of forces. Well, if you think about the wheel as it's rolling down the hill, there was a force of friction pointing up the hill, and then there's part of the weight which points down the hill. The block, on the other hand, is just going to have the downhill force of gravity, but no friction. So in terms of forces, we can say that the wheel experiences friction while the block does not. All right, so the second part of part C wants you to explain your answer again, but this time do it in terms of energy. So here you can say that the two objects are both going to start with the same amount of gravitational potential energy, since they have the same mass and start from the same height. So we have the same initial gravitational potential energy. And then when the objects go down the hill, that potential energy is turned into kinetic energy. However, remember there are two types of kinetic energy. The block is going to have kinetic energy 1/2 mv squared. That's what we call translational kinetic energy. The disk is going to have translational kinetic energy plus also rotational kinetic energy. So some of the potential energy has to go into making the disk rotate, which means there's going to be less kinetic energy left over for the translational motion. So you can just say the wheel has rotational kinetic energy, and the block does not. So since the block doesn't have to spend any of its energy to make it rotate, all of the gravitational potential energy is going to go into the linear motion, so it's going to be moving faster than the wheel when it reaches the bottom of the incline. All right, so that does it for this problem. As usual, let me know if you have any additional questions by sending me a message, and I will try to clear those up. All right, I'll see you back.